Hello again. In this video, we want to show you how to take data from colorimetry, like we've gathered in the last video and sort of introduced the concepts for there, how to turn data like that into a graph, how to make a best fit line again, and then how to use the best fit line to answer a few questions about solutions and unknowns, which is usually the part of the goal, at least with colorimetry and making your original graph and your line of best fit, is so that you can then consider unknowns of that same solute, of that same sort of solution, and be able to determine the concentration of a solution from its absorbance, or maybe predict the absorbance for a particular molarity. We're going to look at varieties of both. And then throughout this assignment, there are also some other questions that ask you about some of the concepts about colorimetry that'll make you probably go back to your notes a bit. So in the previous video, the notes were introduced and they've been shared with you on Google Classroom, so hopefully you have access to those. If you can't find them for some reason on Google Classroom, shoot one of your teachers an email and hopefully we can help you out. Okay, so this assignment that's on the screen here should be one that you picked up, and if not, you can follow along. You can do the answers for these right into your own notes, and then you'll need a piece of graph paper or something close to a graph paper. If you don't have this assignment, do your best to do it even in a notebook page, but graph paper is obviously far better because as we go, we're going to be working with graphs, and it's much easier to make a decent graph like this if you've got graph paper. So do your best if you don't have that, but hopefully you picked one up. And if not, you need to get one from us next week, so it's a little easier to fill in and follow along with, but you're still responsible for what you should be doing as a result. So number one says you were asked to analyze a solution of nickel sulfate, which is an emerald green solution. And each of these problems will tell you about the color of the solution that's being studied, because that's going to help us to answer the very next question. Which color of light would you recommend to be used to study the nickel sulfate solution, which we've said is green? And this is one that was introduced in the first video. So this is kind of a review more than anything. But if you recall, we introduced these notes to you when we were looking at the last video, and we talked about complementary colors. So for a green solution, we want to use its complementary color. Hopefully you can see right here on the slide that the green is across from the red. And so we're going to choose a red wavelength like we did in the last introduction to study this green solution in this problem. So we're going to use a red light to study a green solution. We want to use a complementary opposite color. So as far as filling this in, bring my pen up here, we're going to go ahead and say a red light will work best to study a green solution. And you'll be asked later on why on question D, so we can talk about that now. We're going to help you through all of number one here anyway. So question D here asks, why did you choose the color that you picked? Well, we choose to study any solution, but in this case, a green solution. To study a green solution, we would need to use a complementary color. We should use a complementary color. And the official term you could use here is wavelength, but color is good enough, because this color will be absorbed best. So the color is that color is absorbed most completely. If we choose the same color, we'll have all that light just shine right through and nothing will be absorbed, and that won't help us to tell one green solution from the next. Okay? So a complementary color is most important. And for each of the questions in this packet, you'll need to choose a complementary color. You should look back to that color wheel in your notes. You can just Google really any color wheel and look across it, and you'll find the color that's the best to use there. All right. So any color wheel with primary and secondary colors is going to be good enough for what we're doing here. The instructions say that you prepare solutions of various molarities. You test each solution with a colorimeter to measure the absorbance for each sample. That's what we did in the first video. So if you haven't seen that technique done or the introduction, you need to get back and watch that first video so you understand what the heck this is talking about. Your data is shown in the table below. So we have a little table down here, and like in our first video, we had several molarities, and we have several absorbances that go with those, and the corresponding numbers will be what will turn into our graph. It says your task: carefully plot this data onto the graph after setting up your axes properly. All right. So we need to make sure that our axes, first of all, are assigned right. Which one's molarity, which one's absorbance? And again, we're adjusting the molarities. We're testing various molarities. The instruction says you prepare various molarities. So that's my x. That's my independent variable. And we're measuring the absorbance that comes about as a result of those molarities. So that's our dependent variable, and that's our y-axis. So whatever you're controlling should usually go on the x-axis, and whatever you're measuring as a result should go on the y-axis. So that's how we're going to set this up. Now you want to make sure that you scale your axes big enough so that you can include all of the data that's here, and maybe have a little bit of room to spare, but you don't want to make your graph so small that you only use this light corner of the graph. So as we're setting this up, I'll help you out with a scale on this first one, and maybe it'll help you have an idea of how to approach it for the second one. So if we look at our absorbance, we need to be able to accommodate absorbances from basically 0 as our low all the way up to a high of at least 1.4. Now we're going to go a little higher than that because we want to be able to go beyond the data a little bit if needed, as high as it'll let us go without kind of leaving the graph so small. But I also noticed that over here in one of my questions, it's going to give me, in this follow-up question too, says we're going to need to have an absorbance at least out to 1.5 because that's one of the follow-up questions. So we're going to go ahead and scale our graph paper so that it has enough room for all the data plus maybe a bit more. So on the y-axis, you want to put absorbance over here. Okay, absorbance. And we don't really have a unit for that. Absorbance isn't a number that we measure with, like, joules or degrees Celsius or grams or moles or anything like that. So it's just sort of abbreviated absorbance. Absorbance is calculated using a logarithmic equation. It uses log, and usually when log is introduced into an equation, you don't have units any units left at the end. They sort of get canceled out or used up in that math. As far as the scaling of my graph goes, I'm going to have it go again on the y all the way from the corner 0 up to at least 1.5. And I counted on this side over here, I've got 19 boxes. So I'm going to go ahead and make each one of these little boxes basically worth 0.1. Now you don't have to label them all, but that's kind of my scale. So each box is worth 0.1. I'm going to go ahead and label every fifth box. Okay, so this box is 0.5. 5 boxes up from there is 1.0 for an absorbance. 5 boxes up from there is 1.5 rather for an absorbance. And then the very top one would actually be 1.9. It'd be nice if this was 1 box more, but it's 19. It'll do. Okay. So this will include all of my data. My highest absorbance was 1.3, 1.4 or so, and we've got all that room and a little bit more, which is just right. Okay. Across the bottom, we're gonna put our molarities. So for molarity, the label is moles per liter. You can say M, which is our usual shorthand version, or moles per liter of solution. Either one is good for our units, but you should definitely label the axis with what it is and units that are being used. And then molarity here ranges anywhere from 0 up to about 0.5, okay? And not much beyond that. So as far as setting up our axis down here, again, we're going to call this corner 0. And then I'm going to use about every fourth box, or maybe let's say every fifth box. Now let's go fourth. You'll see why here in a second. But make every fourth box worth 0.1. So this is 0.1 molar. This is 0.2 molar. This is 0.3. 0.4, and again, I'm counting every fourth box, 0.5, and then we can actually have this go as far as 0.7 if we wanted to label it all the way out to there. Okay. So we've used up our graph fairly well, and our data will definitely fit. The furthest out point will be at 0.5 molarity and about 1.36. So it'll be, kind of out here somewhere in the corner of the graph, and that's a good spot for your largest data point, and still uses most of the graph. Okay, so to set the data in here now, we need to recognize just one more thing I'm going to point out, that across our x-axis, the units, each little box is worth 0.025. So this is actually 0.025. This is like 0.05. And then this one is 0.075. Now you don't need to label all those. I just want to show you that since we get these divided down into 4 parts, that's the increments. So 0.025, 0.05, 0.075, 0.1, and then it repeats again. So as we've divided into fourths, that's kind of the increments we're looking at. So our first data point here is 0.025. Well, that was one of the marks I just noted for you. And then 0.071 is the absorbance. So I want to be careful here. 0.025 means we're going to be here. Okay. Oops, I apologize. Here. And then 0.071 is actually way down here in the corner, right? So 0.071 is not 0.7. That would be up here. 0.07 is actually sort of right down here someplace. I'm going to put a dot right there. And you can make them big enough to be seen. Okay? They don't have to be huge. You want to make them precise, but big enough to not get lost, and also small enough that they aren't gaudy and kind of big all over the place. So a precisely plotted point is good. The second data point is 0.075, and an absorbance at 0.075 of 0.2, right around 0.2. Okay, so 0.075 is that's the third little mark over, And 0.2 is the second box up on the y-axis. That puts me right about here. Okay, so 0.075 along my x, and 0.2, just a little bit above that even would be okay for my 0.201 for my absorbance. Okay, so that's my second point. And you'll notice I'm not going to go and put my ordered pairs on here next to them. You certainly can if you wish, but you don't need to. There are certainly places in math where that might be helpful or more required, but we're not going to require that you label your points. So our third point is 0.125, and our absorbance there is 0.335. All right, so 0.125 is here, and 0.335 is, this is 0.3, this is 0.4, so 0.335 is right about here. Okay. Put a dot kind of right about there. Now it seems like we're kind of way down stuck in the corner, but this next one's going to jump us out quite a ways. The next molarity is 0.25 molar, and our absorbance there is 0.689. Okay, so 0.25 puts me way over here. All right, this would be 0.25. And then the absorbance was 0.689. So 0.6 is right about here. 0.7 is right about here. It's pretty close to 0.7, so something like right about there. Right, so 0.689 would be a point right about there. And then our fifth and final data point here is 0.5 molarity on my x-axis and 1.359. Okay, 1.359. So 0.5 molarity would mean I'm on this major line kind of right here. And then 1.359 means I'm going to be somewhere up here. This is 1.3, this is 1.4. So I want to be right about halfway between. 1.359 puts me right about there. Okay. So I'm going to put a dot there. So now if you look at your data here, if you plotted all your data along with us, we've got the line, the points, they're pretty much in a straight line. So what we want to do next after we've plotted them is put in a line of best fit. And these will all be linear best fit lines, so you can just use a ruler or a straight edge to do it. And your points should pretty much line up. You're going to find out that the data we're giving you, it lines up pretty well. And usually colorimetry data does line up pretty well. So a line of best fit is going to be fairly straightforward to draw. As we go through the other three in this packet, you might find that some of them have some points that don't line up quite as perfectly, but do your best to draw a best fit line that kind of goes right through the middle of all the data points you've got. In this case, we've got 5 points. We're going to draw our best fit line sort of right through the middle. Now, I've got a line drawing tool here that I'm going to go to. You might need to use your straight edge or whatever works best for you. And what you also want to be sure to do is extend your line out beyond the data. So don't stop just because the data stops right here. Don't stop your line there. Let's continue it all the way off to the edge of the page. Okay? I'm going to shrink this down just a smidgen, if I can. Well, that's a little too much. All right, something like that. And then I'm going to go ahead and draw my line in here. So I want to draw a straight line through all my points and treat it like I've got a ruler here. Again, I've got a virtual one. And I can go back and change it if I don't like it, which I don't already like it. So as much as these digital ones are nice, they're not always the solution for everything. And I don't care if it goes off your chart a little bit or like so, but that's kind of what we're looking at, right about there, right? So my points here are quite small, and you might find that yours are too, but basically they lie right in line with my best fit line. And if yours is just a little bit positioned differently than mine, it's probably fine. It doesn't have to look exactly like this, but you want it to be straight. And you'll notice that a best fit line for most colorimetry data will pass right through the origin of our graph. It doesn't have to. Note, it does not have to pass through the origin, but it more often than not will. Let's think just for a second about why. If I have a 0 molarity solution, that means there's no solute in it. That means it's just distilled water, right? With nothing in it. That's 0 molar, if there is such a thing. And no solute means nothing's in there for color, and the absorbance will be 0. So 0 molarity and 0 absorbance kind of go together, just makes logical sense. So if you think that, man, all these are going through 0, 0, they need to, they kind of should, but you don't have to do that. If your data says that the line doesn't go through 0, 0 on your origin, then don't force it. But if it often does, as this one seems to for my data, then that's okay because it kind of makes sense that it should. All right. So now the questions that come next: estimate the molarity of a nickel sulfate solution with an absorbance of 0.512. Okay. So what we do here then is kind of straightforward. And what we want to do here is go to our graph at the absorbance of 0.512. So I'm going to change to a red so it pops out a little bit better. Absorbance of 0.512 is going to be somewhere down here, just a little bit above 0.5, right? So 0.51 is probably right about there. And it's what I want to do is read across from there. And you can use your, use your straight edge, use your ruler, whatever. I want to read across to right about here where it intersects my graph. And then I'm going to go down to the bottom and read out what molarity that represents across the bottom. Okay? So 512, 0.512, and you don't need to label these, but I will for the purposes of our first video here. 0.512 absorbance, I go across till it intersect the best fit line, and then I drop down to the x, and this is very basic math interpretation. This hopefully isn't something that's like, wow, I've never seen that before. Of course, you've seen this in things. You've seen it in math classes. We do this with graphing, and if you haven't, hopefully you'll find it isn't too difficult. But if you're not as comfortable with this or familiar as you think you are, then make sure and stop and see one of your teachers about it, because we don't mean to insult your intelligence if you do know how to do this, and we don't mean to make you feel like you're the only person that doesn't know how to read a graph like this if you don't, because some people just haven't seen this as much. But we need to answer the question. So what is the molarity? Well, down here on the x, that's coming in kind of right here. I'd say that's right around 0.19, if I had to guess what that is. That looks like about 0.19 molarity, because this is 0.2 and this is 0.18, and I'm halfway in between, right? So that's about 0.19 molarity. So if I'm going to go up here and put my answer down, I'm going to go ahead and use that. 0.19 molar, okay? 2 decimal places is good enough. You're probably not going to go more precise than that when you're just kind of eyeballing it off of a graph. Okay? Now, I should note, the other way we could do this is take this line that you drew, this best fit line, calculate the slope of that best fit line, and then we'd have a very precise equation from which we could plug in the y and get the x, and have all kinds of decimal places. But it really doesn't matter too much as long as you're sort of close with this, just so that you get the idea of how we use colorimetry and how we use the graph. Okay. Now, the second question asks, estimate the molarity with an absorbance of 1.509. Well, okay, same idea as before. 1.5 is up here on the top, 1.6 is right above it, so 1.509 is just a little bit above 1.5, just kind of right there. Okay? And I want to read across at that point. That's going to read straight across to about here, right? If I follow across, and then that follows down, we want to read down to the bottom and see where that intersects our x-axis. And I'm going to kind of eyeball, because these graph lines make it really easy. That's going to plop me in right about here. Okay, so what does that represent? Well, this is 0.5, this is 0.52, this is 0.54, this is 0.56. And so it's pretty close to 0.5. This is 0.5, oops, I'm sorry. Clean that up. This is 0.54 on that line. This is I'm sorry, I made a mistake. Let's back that up. Okay, this line right next to it would represent 0.55. Right? And so it's a little bit more than 0.5. This line would represent 0.575. And so we're kind of somewhere in between there, and you kind of have to estimate. This looks like about 0.56 or so, I guess is what I would say. So a molarity of about 0.56 molar would be right about there. And so our answer up in the top here could be 0.56 molar. All right. Now I just noticed as I was looking at that one that we kind of misread the other one so slightly, but I think 0.19 is reasonable, because I said this little mark, this main line was actually 0.18, and it's not, it's 0.175. Right? So if you were looking at that and thinking, Beth, you can't even read fractions. For a second there, I had a little bit of momentary lapse in judgment. But this mark is 0.175. I think our little point here is still about right, about 0.19 is reasonable. Okay, so I did see that I made a mistake there. Now, on question 3, what absorbance would you predict for a 0.375 molarity nickel sulfate solution? So that's just the opposite. It's really not any tougher, but 0.375 means, okay, let's go to a molarity of 0.375. That's right here, 0.375. And we're going to just read right up the line. That's nice because we can stay on a nice dark line. That means we come in right about there on our curve, which means I come across then to the y-axis at that point, and it's going to be just a little bit above 1. So if that's 1.0 and this is 1.1, then I think that line's at about 1.03, maybe 1.02 or 1.03. All right. Now, what you'll probably find is if you did this graphing more than once, okay, and you graphed all your data out and you drew a best fit line again all over from scratch, you'd probably find that your best fit line was drawn a little differently the second time, and all these answers would be just a little different the second time, and that's okay. It's also true that if you looked at a classmate's sheet and said, what numbers did you get? If yours are just a little different than theirs, it doesn't mean either one of you is right or wrong. It means you're both in the right ballpark, right? Because how we draw the best fit line is sort of subjective and sort of shows how human we are. We're not going to draw it mathematically perfectly because we draw with a ruler. But if we did have a close molarity or close absorbance compared to someone else looking at the same question, you're probably in great shape. So because there is some subjectivity in how we draw the best fit line, that might be the case that yours might be slightly different than your neighbor's and certainly even slightly different than mine, but they should be pretty much in the same ballpark. Okay? So that's the first problem. That's as far as we're going to go with the video. The next three on the sheet take you into different solutions, give you different numbers, ask you different questions at the end, and then the follow-up question on each one is that question D that makes you think a little bit about the notes again and a little bit about the concept of colorimetry. So question one, A, B, and C, it all looks pretty much the same. Question D on each problem is just a little different. Answer those to the best of your ability. Get your data plotted. Answer the questions 1, 2, and 3 here where we ask you to do some estimating. And we'll see how you do when you come back to class next time. Thanks for listening. Good luck.